Alrighty, folks, here. Welcome to the Crazy Hat Chemist. And today we are doing the third video in this series of chemical reactions. And today's video is going to be predominantly focused on net ionic equations. And let me preface this with if you are not in my class, then I'm just letting you know that all the net ionic equations that we'll be doing today are double displacement, double replacement equations. It doesn't mean that all net ionic equations are double displacement. It just so happens that on this worksheet, all the equations of which are on this worksheet are double displacement, double replacement, just so that you know. So I'm trying to follow a pattern. Again, I highly recommend that you know your unit for nomenclature. That is essential, and that you are knowing when your nomenclature unit and the chemical reactions video. And I gave two really good examples of how to do net ionic equations in my video series, the lecture video series, that is. You are watching the worked out solution series. So here we go. Let's get moving. Directions for the next set of reactions, and there are 10 of them. Write only the net ionic equations, canceling out the common or spectator ions. For the following, refer to solubility rules to determine the product. Okay, and here we go. It says silver nitrate is poured into a beaker containing sodium bromide. So silver is a 1+ cation, like that, and nitrate is a polyatomic ion. That's NO3 1-. Sodium is a group 1, and bromide is a halide ion and a -1 charge. So that's what we got there. So we're going to put these two things together, This is the double displacement, double replacement absolute value of these numbers. Flip and bring it down. So I get AgNO3. All nitrates are soluble. I'm referring to my solubility rules. And then NaBr, anything with sodium in it, is soluble and aqueous. Since it's a double displacement, double replacement reaction, the silver is going to combine with the bromide and the sodium with the nitrate, just like that. So sodium nitrate, and that's Na1NO3. All sodiums and all nitrates are aqueous. So there we go, just like that. And then silver bromide, that's also a 1-to-1 ratio. That's AgBr. And bromides, chlorides, and iodides are aqueous, except for silver, mercurous, and plumbous. So therefore, this is a solid. So now what you're supposed to do is write out the total ionic equation. Okay. Oh, by the way, we do need to balance this. This particular one has stoichiometric coefficients of 1s everywhere. So 1, 1, 1, 1, it is balanced. So then the next thing that we need to do is we need to write the total ionic equation. So if it is aqueous, then you break it apart into its ions. So we're going to do Ag1+ aqueous. This is going to be quite tedious, but it works really well. NO3 -1 aqueous plus Na1+ aqueous plus Br 1- aqueous. And then Na1+ aqueous. And then NO3 -1 aqueous. And then if it's a solid, liquid or a gas, you keep it together, and that would be AgBr, and that is a solid. So this is called the total ionic equation right here that we see. And now what we're going to do is we are going to cancel out, and that's what this says, canceling out the common or spectator ions. Common or spectator ions. Spectator ions are common ions. What are the common ions or spectator ions? Well, they must be the same on both the reactant and product side. So exactly the same in its state of matter. They're both +1, they're both aqueous, and there's 1 and 1. So they cancel out. And then also the nitrates. So what are the common or the spectator ions? The sodium ions and the nitrate ions. And then we're going to drop down everything that we didn't cancel out, and that will be our net ionic equation. So that will be Ag1+ aqueous plus Br 1- aqueous yields AgBr solid, just like that. Okay, fantastic. And in my video series for the lecture, I've shown you another way to go about doing this, and I'll just briefly mention that right here. So what you do is a shortcut is to take the product that you know is insoluble and write that and then decompose it. That is, take this apart into its cation and anion form and gonna go backwards. And then anything that is not involved in that would be your common or spectator ions. All right? Fantastic. So now what we're going to do is we're going to scroll this up so that we can see number 2. Yes, that's right, folks. There's number 2. All right. So number 2 is the following. 2 test tubes are mixed, one containing barium chloride, the other containing sodium sulfate. So barium is a 2+, and chloride is a halide ion, 1-. Sodium is a 1+, and sulfate is SO4, 2-, just like that. All right, so we're going to take the barium chloride. Chlorides, bromides, and iodides are aqueous except for certain ones, silver, mercurous, and plumbus. And then sodium sulfate. And sodium is aqueous, period. End of story. There's a double displacement, double replacement, like every single one of the reactions on this worksheet. And then we're going to combine the sodium chloride and then the barium sulfate together. It doesn't matter which one you write first, which one you write second. I'm going to write the barium sulfate here. And sulfates are aqueous except for barium, strontium, lead, and calcium. So therefore, this is solid. And then you have NaCl. And this is aqueous because anything with sodium in it is aqueous. We need to balance this. There are 2 chlorines and 2 sodiums and 1 on the product side, and now that is balanced. All right, so the next step is to write the total ionic equation. The total ionic equation is taking everything that is aqueous and breaking it apart and leaving the thing that is a solid all to itself. So that is Ba2+ aqueous plus 2 chloride ions, that's aqueous, plus 2 sodium ions, aqueous, and 1 sulfate, aqueous, yields barium sulfate, and that is my product that is insoluble, plus 2 sodium ions, aqueous, and 2 chloride ions, aqueous. Okay, so hopefully you see everything right there. Again, now what we're going to do is we're going to cross out or cancel out the common or spectator ions. That's 2 chlorides, 2 chlorides, 2 sodiums, 2 sodiums. And what remains is what I'm going to drop down on the reactant and product side. So I'm going to have Ba2+ aqueous plus SO4 aqueous, that's 2-, yielding BaSO4 solid. All right, fantastic. That's number 2. So let's move this on up to do number 3. All right, so let's see if we can get this moving here, get it straightened up. All right, perfecto. It says a beaker of ferric chloride is added to a beaker containing calcium hydroxide, and it does say a solution of, so that means it's a solution of. Yeah. Oh, this video here is brought to you by the Crazy Hat Chemist. Okay. Yes, please subscribe and like, or like and subscribe, whatever you want to do in whatever order, it doesn't really matter to you. Okay. Here we go. Ferric chloride, that's Fe3+ and Cl1- for the chloride, and calcium, that's group 2, and hydroxide, that's OH1-. So FeCl3, that's aqueous. Chlorides, bromides, and iodides are aqueous, okay, except for silver, mercurous, and plumbus. And then Ca parentheses OH Na2, and that is aqueous because it did say it's a solution. I'm going to combine the ferric and the hydroxide and the calcium and the chloride. There's the calcium chloride, that's aqueous, and then the ferric hydroxide. And hydroxides are insoluble except for ammonium ion and the alkali metal, so therefore that is insoluble. Now what we need to do is balance this beast. We got 2 chlorines and 3 chlorines, so we're going to put a 3 here and a 2 here and a 2 here and a 3 here, and then that will be balanced. This is going to be quite a bit of a mess. Remember, all the ones with the aqueous are going to be broken apart into their ions. So 2Fe3+, that's aqueous, plus Now it's going to be 6Cl1 minus aqueous plus 3Ca2 plus aqueous plus 6OH1 minus aqueous yields 3Ca2 plus aqueous plus 6Cl1 minus aqueous and plus 2FeOH3 solid. We're barely making it on the paper there. Okay, so we've got 6 chlorides. 6 chlorides, those are common or spectator ions. 3 calcium ions, 3 calcium ions. Perfect. And now what we're going to do is we're going to have 2Fe3 plus, that's aqueous, and plus 6OH1 minus, that's aqueous, yielding 2FeOH3 and solid. Now, one thing that we do need to do at this point in time is we do need to reduce because we need to have the lowest stoichiometric coefficient. So this is a 2, that's a 6, that's a 2. So this is going to be 2, it's going to divide evenly into the 2, the 6, and the 2. So this will end with a 1, and this will end with a 1 right here, and then this will be a 3 there like that. Okay, so we're going to have Fe3 plus aqueous plus 3OH aqueous yielding FeOH3 solid, and that will be my ending result. Okay, fantastic. Hopefully you got that. That's looking just peachy fine there. That's number 3. We've got 7 more to do. So let's peel this away and then go back up to the top of another sheet of paper. And let's see if we can hammer out problem number 4. Says phosphoric acid is added to sodium hydroxide. Fantastic. You got a couple of other little bits there and parts there. Phosphoric acid is the phosphate ion, and all acids have hydrogen. And then sodium is group 1, and hydroxide is a polyatomic ion. So H3PO4, that's aqueous, and NaOH, and anything with sodium is aqueous. This is a characteristic acid-base problem here, and the acid and then the base. And so we are going to have the sodium phosphate and then the hydrogen and the hydroxide. So the sodium phosphate is aqueous, and then the HOH, that's water, and you could have written that as H2O, and that would have been perfectly fine, but that's a liquid that's not following solubility rules. There are 3 sodiums, and then 3 waters. They're like that, and that would balance that out perfectly fine. Okay, fantastic. So now what we need to do is break apart all the ions in solution. So we're having 3H1 plus aqueous and plus 1 phosphate, that's aqueous, plus 3Na1 plus aqueous, plus 3OH1 minus aqueous, yielding 3Na1 plus aqueous, plus PO4, 3 minus aqueous, and plus 3H2O, and that's a liquid. All right, I'm going to cross out my common, whoops, let me slide that over there. I'm going to cross out my common or spectator ions, that's sodium ion and the phosphate ion. I'm left with 3H1 plus aqueous plus 3OH1 minus aqueous, yielding 3H2O liquid. And like we did on the last one, we're going to reduce these stoichiometric coefficients to the lowest whole numbers. And that is H1 plus aqueous plus OH, 1 minus aqueous, yielding H2O liquid. In fact, every acid-based problem is going to have this same characteristic pattern of a hydrogen ion, a hydroxide ion, yielding water. That's what an acid-based problem is going to be. And it is not following solubility rules. It is a liquid in solution. All right, cool. We're going to move this on up to do problem number 5. So stay alive with problem number 5, folks. Okay, here we go. Number 5. Let's see. We have barium acetate is mixed with sodium fluoride. So barium, that's a 2+, and acetate CH3COO 1-, sodium group 1+1 fluoride halide ion, just like that. Okay. All right, so we got barium acetate. That's aqueous. All acetates are aqueous. We got sodium fluoride. Anything with sodium in it is aqueous. Again, all of these on this whole entire sheet of paper here of all these 10 problems are double displacement, double replacement reactions. We have barium fluoride as my product. That is the cation and anion going to get together there. Fluorides are soluble except for a small group of them, of which this is going to be insoluble. So, and then we have sodium acetate. And that's also aqueous because it has sodium or acetate in it. We're going to have a 2 right there and a 2 right there for our balancing. Then we're going to write our total ionic equation. So that's a Ba2+, that's aqueous. And 2CH3COO1-, that's aqueous, and plus 2Na1+, that's aqueous, plus 2F1-, that's aqueous, yielding BaF2 solid plus 2Na1+ aqueous. And I'm going to run out of space, but we're going to put it right down here. 2CH3COO1- aqueous. Okay, so we're going to cross out our common or spectator ions. That would be the acetate. That would be the sodium ion. And then what remains is the Ba2+ aqueous plus 2F1- aqueous, yielding BaF2 solid. And that is my total ionic equation in the blue, crossing out the common or spectator ions, and then the net ionic equation in the red right there. All right, hands down, that's an awesome problem, folks. Here we go. All right, so now we're going to move on to our next problem. Our next problem is right here with number 6. Number 6, here we go, number 6. We have a beaker containing ferrous iodide is mixed with calcium oxalate. So ferrous iodide, ferrous is 2+, iodide is 1-, that's a halide ion, calcium is a group 2, that's +2, oxalate C2O4 and a 2-. So we're going to have FeI2, that's aqueous, plus Ca C2O4, that's a 1-to-1 ratio, that's also aqueous, yields FeC2O4, and that is a solid, plus CaI2, and that's aqueous. All right, so you should see that we need to do just, no, this is already balanced, so that's super spamtastic. Super spamtastic. All right, so here we go. We're going to do the total ionic equation, and that's going to be Fe2+, that's aqueous, plus 2I1- aqueous, plus Ca2+ aqueous, plus C2O4 2- aqueous, yielding FeC2O4 solid, plus Ca2+ aqueous, plus 2I1- aqueous. All right, I think we fit that all on there. We're going to cross out our common or spectator ions, and that's the calcium ion, the iodide ion, and then we're going to drop down what remains. That's Fe2+, that's aqueous, plus the C2O4 2- aqueous, yielding our ferrous oxalate, which is a insoluble precipitate. All right, fantastic. That was number 6. We are more than halfway done now, so we should be feeling really good now. All right, so I'm going to peel this away and go on to the next problem. Okay, we've got 4 more to do, I believe. So, starting with number 7, a poisonous solution of mercurous chlorate is mixed with ammonium bromide to precipitate the poison. Okay. Okay, mercurous, that's Hg2 plus 2. And then chlorate. What's chlorate? That is ClO3, 1 minus, and then ammonium ion is NH4, 1 plus, and then bromide is Br, 1 minus, there like that. All right, so we have Hg2, ClO3 parentheses and a 2, that's going to be aqueous. Chlorates are aqueous, and then ammonium bromide, and anything with ammonium in it is aqueous. And then so now we're going to combine these two things together. That's ammonium chlorate, that's aqueous. And then we have mercurous bromide. Hg2Br2, and that is our solid insoluble precipitate. We're going to put a, what are we going to do? We're going to put a 2 right here and a 2 right there, and then we got a great balancing going on, act. So we're going to have Hg2, 2 plus, that's aqueous, and plus 2 ClO3, 1 minus aqueous, plus 2 ammonium ions, aqueous, plus 2 bromide ions, aqueous. And then I'm going to put the arrow right down here, 2 ammonium ions, in hopes that I might be able to actually put this all on one line, plus 2 ClO3, 1 minus aqueous, plus Hg2Br2 solid. I made it. Fantastic. This is the total ionic equation. I'm going to cancel out my common ions of chlorate and ammonium ion. And then I'm going to have Hg2, 2 plus, that's aqueous, plus 2Br, 1 minus aqueous, giving me Hg2Br2, and that's my insoluble precipitate, my net ionic equation. Oh yeah, baby, looking good. All right. So what we're going to do is we're going to move this on up here, and we're going to do number 8. All right. So number 8. Here we go. Plumbic nitrate is mixed with potassium chromate. All right. So plumbic, that's Pb4 plus. Nitrate is NO3, 1 minus. Potassium group 1, 1 plus. Chromate is CrO4, 2 minus. So we have plumbic nitrate, PbNO3, 4. All nitrates are aqueous. Plus K2CrO4, aqueous, yielding the plumbic and the chromate are going to get together, and you're going to have to reduce this formula. So you get PbCrO4, 2, and chromates are insoluble except for ammonium ion and alkali metals. And then KNO3, and that's aqueous because anything with potassium is aqueous. Anything with, yeah, so that's looking good. And now what I'm going to do is I'm going to teach you yeah, so here we go. We're going to balance this. We got 4 nitrates, so 4 nitrates over there, 4 potassiums, now 4 potassiums, and then that's looking balanced there to me. So now what we're going to do is we're going to write the total ionic equation. So that's Pb4 plus aqueous plus 4NO3, 1 minus aqueous, plus 4K, 1 plus aqueous, plus 2CrO4, 2 minus aqueous. And we're going to draw this arrow right below here again. And we're going to get PbCrO4, 2, that's our solid, plus 4K1 plus aqueous, plus 4NO3 minus 1 aqueous. Okay. So what we're going to do, we're going to cross out our common or spectator ions. That's the 4 nitrates and the 4 potassium ions. Now I'm going to have Pb4 plus aqueous plus 2CrO4, 2 minus aqueous, yielding PbCrO4, 2 solid. Okay, fantastic. We have 2 more to do. That's it. So we're going to slide this on up. And where are we? Here we go. Number 9. Number 9. All right, so number 9, we've got a solution of ammonium sulfate is mixed with a solution of strontium perchlorate. Okay, so ammonium ion, NH4 1 plus, and sulfate is SO4 2 minus. Strontium is SR 2 plus, and perchlorate is ClO4 1 minus. Okay, so again, double displacement, double replacement on every single one of these. So we're going to have NH4 parentheses 2SO4. Anything with ammonium ion in it is aqueous, plus SR ClO4 2. Anything with perchlorate are aqueous. And double displacement, so the ammonium and the perchlorate are going to get together, and that's the ammonium perchlorate, ClO4, and that's aqueous, oh yeah. And then strontium sulfate, so that's SrSO4, and that's a solid. So sulfates are soluble except for barium, strontium, lead, and sometimes calcium. So we need to balance this. We're going to put a 2 in front of the ammonium perchlorate, and then what we're going to do is write our total ionic equation here. So 2 ammonium ions, that's aqueous, 1 sulfate ion, that's aqueous, 1 strontium ion, that's aqueous, 2 perchlorate ions, that's aqueous, yielding 2 ammonium ions, and 2 perchlorate ions, and then plus our insoluble precipitate of the strontium sulfate. So we're going to cross out our spectator common ions, and that's the 2 ammonium ions and the 2 perchlorate ions, and we're left with the sulfate ion and the strontium ion, which of course both of them are aqueous, and then we get strontium sulfate as our insoluble precipitate. Boom! All right, so we have 1 more to do. Let me slide this over just a little bit, so I just barely touched upon that aqueous on that one. We have 1 more to do, and I think we might be able to do it here. If we can. I think we can. So we're going to put that off to the side here. And we're going to do our very last problem here. Here we go. And it says a beaker of aqueous potassium chromate is added to a solution of cuprous chloride. So potassium is +1, carbonate is CO3 2 minus, and cuprous, that's Cu1 plus, and chloride is Cl1 minus. Did you know that all my videos are sponsored by the Crazy Hat Chemist? That's right, folks, the Crazy Hat Chemist. Subscribe and like if you're learning anything, or surely pass this on to all your friends. All right, so here we go. Double displacement, double replacement reaction, K2CO3. That's aqueous. Anything with potassium in it is aqueous. And then CuCl. And chlorides, bromides, and iodides are aqueous except for certain ones, which are silver, mercurous, and plumbous. That is not. So potassium and chloride are going to get together. That's KCl. That's going to be aqueous, most certainly. And then the copper and the carbonate are going to get together. So that's Cu2CO3, and that's a solid because carbonates are insoluble except for group 1, that is the alkali metals, or ammonium ion, and this is not it. So there's 2 of those and 2 of these. That's balanced. Now we're going to write the total ionic equation. So that's 2K1 plus aqueous plus CO3 2 minus aqueous plus 2Cu1 plus aqueous and plus 2Cl1 minus aqueous, yielding 2K1 plus aqueous plus 2Cl1 minus aqueous plus C2CO3, CuC2O3 solid. And we're going to cross out our common ions, and that would be the potassium ion and the chloride ion. And then what remains is the carbonate ion, that's aqueous, and 2 copper ions, 2 cuprous ions, of course is aqueous, and then you get cuprous carbonate. That's an insoluble precipitate. Right. And I'm going to do one more thing here before we just completely end this problem, and that is the following. There's another way to do this, and I did mention it, and so we're going to work with it for this one. If we have this part and we don't need to write down the common or spectator ions or actually write out the total ionic equation, what we can do is take this and bring this down. Cu2CO3, that's a solid. And now I'm going to kind of like decompose this. I'm going to break it down into its constituent components. And that is, what made this cuprous carbonate? It must be a cation and an anion. It must be the copper. And what's the charge on this copper? It's a 1 plus. How many coppers? There's 2 of them. And it's aqueous, always on the reactant side. Then I have a carbonate, and that's a 2 minus, and that's aqueous, and there's 1 of those. And now I have the net ionic equation just by taking the product that's an insoluble or the liquid water, and then I get the following. And that's another way of doing that. So hopefully that makes sense. Again, please, if you are learning some good chemistry stuff here, please like and subscribe. I greatly appreciate that. I am the Crazy Hat Chemist. I hope you have a fantastic day, and I will see you next time for another awesome video. That is it for now. See you later. Hasta luego.